Okay, everybody. This is going to be your next video for at least this little series is going to be membrane permeability. So now that you have a little bit of background on the phospholipid bilayer as well as how the um, phospholipids are oriented with the tails facing each other with the non-polar sides and the polar sides, right? The polar heads. Uh, we're going to have to go talk about how one thing gets from one side to the other, right? So we're going to talk about selective permeability and how exactly like what can go through easily and then what other items might need to go through, specifically membrane proteins. If you go take a look at these essential knowledges, it basically tells you what can go through on one side and the other. We'll explain why, and we'll kind of draw some pictures so you can see. And we're also going to go talk a little bit about some cell walls. Cell walls kind of throw people off because it still works as a boundary, but it's not a phospholipid bilayer. It's a carbohydrate layer. So it's kind of like, what does that look like? Okay. So in the case here, all organic molecules need food and water. So let's go ahead and kind of take a look at some of these things real quickly, okay? So you can probably go take a look and be like, okay, well, what are some of the things that we're going to go need, right? So this is oxygen gas, right? So we need oxygen in order to go ahead and breathe in, so you need oxygen gas. This guy right here is water. We're going to need to make sure that we get enough water inside and outside. If you're dehydrated, you need to drink water, and it rehydrates you, right? What's happening is the water is going inside of your cells, and that's what causes you not to be dehydrated anymore. You got this glucose right here, so we know that glucose is the molecule that's associated with all energy functions, specifically in cellular respiration, and we make it in photosynthesis. This is the stuff that is there in order to power up your cells. Um, then we have nitrogen gas. So this is nitrogen gas. Nitrogen gas is a little bit weird because you don't really actively use nitrogen gas. Specifically, it's nitrates and nitrites. So NO2, NO3, that's your nitrates and nitrites. Specifically, these are the ones that are going to be going into the plants, and they help out in building, specifically the nitrogen base biomolecules. So that's going to be your DNA, right? The CHON and CHOMP, so your DNA and your amino acids, your proteins. And then finally, you have carbon dioxide, right? Now, keep in mind, carbon dioxide, this is a waste product, right? That needs to be removed from your cell. So how does it get out? And just a little bit of a peek behind the curtain is that the glucose is what eventually becomes the carbon dioxide. So when we break this down, you're going to go chemically alter it, and you can kind of see where you can see carbons and oxygens specifically in this molecule, right there, on how that ends up happening. A little bit more stuff ends up happening, but it's my way of kind of alluding you into it. Okay, now the first thing that we're going to go do is talk about selectively permeability. Okay, now selectively permeability basically means is that the cell is going to be picky about what can go through the membrane. Okay. There are certain things that have an easier time to go through the membrane. There are certain things that are not able to go through the membrane. Okay, and when it comes down to it, if we need to go and get the stuff in, we have to come up with two different methods to bring the stuff in. And we're going to go talk about this when we hit our diffusion unit, which we'll get around to it. The first option, I'm going to start off with this, is that we can go right through the phospholipids. Basically, if the thing is small enough, it can go ahead and squeeze right through and get to the other side of it, right? So we have this little dot right here. It goes through and eventually goes through the other side of the membrane, right? And then it can end up, popping up over to there. The other option is that, well, let's say that we have a molecule that is too big, right? So we have this big molecule right there, and it can't fit through the phospholipid bilayer. Well, instead, we're going to go use a protein channel. So we're going to go through the protein channel. And basically, as long as you have a protein channel for a specific molecule, and I'm going to go, we'll talk about this later on, but it has to be for a specific molecule. Specific molecule. Right? So certain protein channels, protein pumps, they'll only let one specific thing in their design, right? Remember, we go saying, right, that structure and function, right? Structure determines function, right? So it's going to be like a 1-for-1 in that case. But these are the two different ways that we can let things in and out. And then other things we might not just be able to get into our cells, and there's no way for it to go. So maybe we end up having I don't know, for a hypothetical scenario that we have like this big molecule right here that there's no way for it to get through. It can't go through the channel. So how do we get through it? It might not be able to get through. And this goes back to what we're talking about, like our selectively permeability, right? We're letting certain things in. We're being picky about what can go through the membrane. So, certain things can go in and other things can not. Okay. When it comes to this, cell membranes are acting like barriers, okay? And when we're saying like barriers, you want to kind of like think about it like, it's a barrier, right? Like imagine like you're out on a castle wall, right? And you got like, people trying to invade or something like that, right? It's, when you say like, you can come in, right? That's perfectly fine, right? But then if maybe in the case here, and if it's like some of the case, like maybe, I don't know, it's like, some kind of like invader or something like that, right? Like a little barbarian or something like that is like, you can't come in, right? And we're not going to allow them to go in. So the idea is that it's going to act like a barrier that's going to allow certain things in and certain things out, right? That selective permeability. Just kind of giving you an idea is that the environments will not be the same, right? If we go and think about the cell, for example, right, here's the cell. Well, what's on the outside, right? Well, if we go and take a look at the outside of the cell, right, it's a completely different environment compared to the inside of it. So there might be specific things that are on the outside, right, like bacteria or nasty chemicals and God forbid, like viruses and stuff like that, right? Now viruses will have their own thing, but humor me for a second, right? We don't want these things inside, right? So we're going to try to keep them outside, right? We do not want them to come inside of the cell. Other things are maybe times like we're trying to pump things in and we want to keep them there. So let's go and take a look at some scenarios right here, right? This is right here. This is actually inside of the mitochondria. This is the electron transport chain, or the ETC for short. And what we do here is that we're trying to pump these hydrogen ions into here to build a concentration gradient in order to go and force them out to go make energy out of it. We're going to go in way more detail about this in our third unit in November. But this is actually probably like one of the most fascinating things where we can see us trying to pump these ions to one side and the other in order to go and harness energy. This would not be useful if the hydrogens were able to just leak on out through the other side. So what we're doing is that we're trying to create a lot of them here, right, by putting them in this little tiny barrier. Then we're just trying to release the energy as we can need it. This right here can show you an image of just a regular cell membrane where you have the extracellular fluid or water or whatever, the blood that's around it, and then the cytoplasm, right? So we want to make sure that nothing nasty gets inside of our cells if it can be avoided. So because of it being fluid, there are certain things that have the ability to move through the cell membrane easier than others. And it actually has to go about with its polarity. I'm going to go right into the next one. Now, what is unique about this is that you got these guys here. So N2, O2, and CO2. These are small and non-polar molecules, and they go across the membrane. So these guys we can see here, right? Here's our O2, right? The O2 can go over to here, right? We have CO2 maybe being created, so that can end up being left. And then like water, like we need to bring water in. Well, water's gonna be a small polar. We're gonna talk about that guy in a little bit. But then like other things like N2, right? If like, I don't know, if we had to go get nitrogen gas in here, like it can actually go right through here. Now let's actually explain why. I'm going to draw it over here. Um, so what causes things to be nonpolar, right, is it's all about the electrons, right? So if I look at nitrogen gas, from your time of chemistry, we know that this right over here is exactly the same as this over to here. So the pool of electrons in this direction is absolutely the same as the pool of electrons in that direction, right? If we go take a look at oxygen, same thing, right? We know that this is exactly the same as this one located over there. So the pool of electrons is equal in both ways. And for carbon dioxide, we have carbon here with dioxide, right? Same thing. This over here is exactly the same as this over to here, right? And what that is doing is that is making it so that way that there is an equal pool on both sides. Now, because of this, all of these guys are going to be non-polar, right? So they're all non-polar. And let's go take a look, right? Well, what do you know about this region where all the phospholipid tails are? This area is non-polar. So because that's non-polar, they're able to slip right on through, and they're able to go through very, very, very easily, right? It works pretty well. They're able to go right through. They don't need some transport protein or anything like that in order to go through. Now, in the case of water, I did make a little note here. Like water can go through the membrane, but the problem is, and like this is kind of like highlighted right here, is that a what is it? Yeah, hydrophilic substance can move across the membrane through channels and transport proteins, right? They can go through there. So we're not really seeing like a transport protein right here. There is a chance that these small molecules can go through, like water can go through the membrane, but it's very, it has a harder time with it. And I'll go draw this one over here. Because if we look at water, right, and you can see like this is what it ends up looking like, right? And you might say, well, wait a second, isn't the one side more equal than the other? But keep in mind, right, um, oxygen is way more electronegative than the other ones, right? Because it has all these free electrons that are hanging out over here. So because of that, there's actually an overall net charge. So there's a minus side over here and a plus side over there. So that means that we are now having a polar item, right? We're having a polar guy trying to move its way across the membrane, which is going to be hard because, again, do polar and nonpolar play? They don't. Polar does not like nonpolar, right? We don't want to deal with them at all. So the water molecules can kind of squeak through, but it's very ineffective. So instead, what we do is that we just basically create a hole, like a channel, right, inside of the membrane protein, and we're able to let the water go from one side to another. We call this an aquaporin. Aquaporin. Which we'll go into more detail when we start talking about osmosis, but that allows us to get smaller hydrophilic stuff in there. This also works in the case right here. We can see glucose. Glucose is going to go through this carrier protein right here. It goes through, and then eventually it pops out over to the other side, and we're able to go ahead and use that. You're going to see different terms: carrier proteins, channel proteins, and transport protein. The way that I kind of describe it to help out with people is that all these are transport proteins, right? A transport protein will end up being used to transfer one thing to another. It's just, is it a channel or is it a carrier? Um, so the carrier usually means like it's like either like one way or it needs energy, right? So it's like we're just trying to pump stuff in one direction or the other. A channel, it's always open. Right. So, what way are we getting it through? So in the case here, we probably want to make sure that we're actually pumping the glucose in. So I'd rather not have a channel. So that way the glucose can just kind of leak out. So instead, I'm just going to try to have it land within this carrier protein. That way I can actually, pump it into the cell. This is what I was talking about earlier, where your water molecules can go through the membrane. It's not super effective, but it can happen, but it's just not really helpful. So instead, we like to use those aquaporins. I'm gonna go ahead and move on to the next one. Right. The last thing we'll be talking about is a little bit about cell walls. Now, this is where kind of people get confused a little bit, and I don't blame you. Even I kind of have to brush up on this a little bit each year. Is that cell walls, right? So let's talk about them, right? What do? They're for structural purposes, and they do have a little bit of permeability. So these cell walls are specifically found, and this says in the next one, it's found in fungi, it's found in some bacteria, and finally, it's found in plants, right? Now, your cell walls are all basically made out of carbohydrates, right? It's all carbs, right? It's all carbohydrates is what this ends up being made out of. So we do have to be able to allow for water to enter through it. And more or less the way I kind of describe it is that there's just little tiny holes or pockets in between all the layers of the cellulose or the cell wall, the chitin that you're able to just move through. And we'll show you that in a second. Okay. Oh my gosh, is this working? Oh, let me out. Let me out. All right, there it goes. All right. And then this is just showing you your different examples of your different types of cell walls that you have here. So chitin specifically found in your fungi, and all it ends up happening is that it's just like it looks slightly a little bit different. It looks slightly a little bit different compared to this cellulose that's found over to here. And then this guy right here, this is peptoglycan. This is specifically found within bacteria. So is your bacteria. Um, this is your plants, and then these are your fungi right here. Um, but overall, right, like it's just the overall the overall structure is a little bit different, but we can definitely see like, hey, look, there's like we can see like, okay, cool, there is our line of carbohydrates. Here we can see our lines of carbohydrates. Right here we can see our lines of carbohydrates. So what I just kind of want you to kind of think about is that the water molecules can and other stuff can still kind of squeak on through here, right? It has some membrane permeability where, let's say like this is my, I'm trying to get my water molecule right here. I'm drawing it up for you. But like here's my like water molecule right here, right? And you can kind of see or use your imagination. If you're looking at this as the cell wall, I can still have this like kind of squeak on by in between these layers of carbohydrates in order to allow the water to get through. I can let it squeak on through here to have the water go through it. And if you can imagine, there's multiple rows of this, I can have it squeak on through in between the areas there. So it does provide some protection. It does prevent certain things from being able to come in, but small molecules still have an easy time, or small nonpolar molecules can still sneak on through there, right? So that's all this was about, is just talking a little bit, letting you know that your membranes are able to allow certain things in and out. So that's it, everybody. uh, Enjoy your weekend, and I will catch you on the next one.